So my name is Andrew Peterson. I'm the water treatment specialist with Eagle. Um, just a little bit about myself. Came into drinking water sort of in a non-typical career path. I spent the first 11 years of my career working in environmental remediation, doing a lot of pump and treat systems. So in that business, a lot of the treatment involved granulated activated carbon and ion exchange, and we did do a fair amount of filtration as well. Um, and a lot of the technologies that are used in environmental remediation are now becoming more prevalent in drinking water due to emerging contaminants. And so that's sort of how I found my way into this water treatment specialist role with Eagle. Um, The topic of today's presentation is coagulation, mixing, and sedimentation. And before we get started, I just want to clarify that for today, we're going to be focusing on coagulation and flocculation and sedimentation as it pertains to conventional and direct filtration with conventional filters that are using granulated media. Some plants do use coagulation, flocculation, sedimentation ahead of membrane filters. It's a little bit different, and we're not going to get into that discussion because it's, as far as I know, there are no plants in Michigan that actually use that process ahead of their membranes. So it's not really very applicable for this audience.
Hey, Andrew.
Yeah, yeah,
So just before you get into your presentation, one more thing I got to do is run a first poll question. So I don't want to break it up too much. Sorry about that. I meant to start it right before you got on, but I'll let you introduce yourself there. So
no problem.
you
Go
good with
ahead and
that? All right. And plus
yeah.
everybody's asking. So
Uh,
our attendees already remember that we got to have a poll question. So I'm gonna throw it up there right now, everybody. So it's the first poll question. Remember, you got to answer these to get CECs. We'll leave it up there for about a minute. And I just want to know how many people are viewing the webinar at your device. So maybe there's more people watching it than just you. If there are, remember, if you want CECs, you got to be logged in as yourself. So you should be really watching it on your own. Okay, actually, it looks like we got pretty much everyone, almost everyone answering the question. So I'll give you another 5 seconds for a couple of people that may or may not need to answer it. All righty, I'm gonna end the poll then, Andrew, and go ahead and continue on. Thanks.
Yeah, no problem. All right, well, I think we're ready to jump in, and I'm gonna go ahead and turn off my video. Okay, so I think this is a great quote to start the presentation off. It says, "The most important factor in plant performance is the use of the optimal coagulant dosages in the pretreatment process." So this is from the AWWA, and I think it's important to realize at the beginning of this presentation that coagulation is what's going to allow the subsequent treatment processes to perform properly. Without proper coagulation, we're not going to get floc formation, which is going to affect our settling in a conventional plant, and our filtration in a direct filtration plant. And also, even in a conventional plant, if you don't have proper coagulation, your filters aren't going to perform well because granulated media filters function based on the principle of particle attachment rather than straining like a membrane filter. So with a granulated filter, we're not excluding particles because they can't fit through the pore space. The particles are actually becoming attached to the filter media. And without coagulation, they're not going to become attached, and they're going to be able to easily migrate through the pore space of the filter media. So it's kind of like the foundation of a house. It's the foundation of our treatment process. And if it's not optimized, then we're not going to be able to optimize any of the subsequent steps. And if the coagulation is so poor, then the subsequent steps may not even work at all, you know. So it's really key. It's one of the first steps in the treatment process, and it's really the foundation for all of the subsequent steps. And we're going to get into why throughout this presentation. Also, I'll just mention, you can see that there are going to be a lot of graphics in this presentation, and that's because the particles that we're discussing today are so small, they can't even be seen with a microscope. And it can be kind of hard, at least for me, to really understand or visualize what we're talking about without some graphics. So we're going to try a variety of graphics to see if maybe one of them clicks with you and helps you better understand what we're talking about today. And this first one that we're looking at is just very general. We see some particles on the left side. And then on the right side, apparently we're using alum. You can see the aluminum ion, and this is something that we'll be talking about. You'll notice the 3+ signs next to it. It's got 3 positive charges. They'll call that a trivalent metal. So at any rate, this graphic's pretty simple, but as we go through the presentation, we'll get into some that are a little bit more detailed. So at the highest level, what is coagulation? It's the process by which small particles are combined to form larger aggregates. And what are these small particles that we're talking about? Well, it's clays and sands and colloids, and it's going to be minerals, and it's going to be organic carbon, and a lot of materials that are from plant, animal, and human activities. And, you know, you're also going to end up having some bacteria and algae and protozoa and even viruses that are either attached to these particles or also suspended in the water column that are going to be impacted by this coagulation process as well. I like this graphic because it shows the coagulant as these little stars. It's kind of our the magic, I guess, that we're adding to this process. Again, you can kind of see they're going to use a variety of different terms for these particles. You'll hear them called colloids, you'll hear them called impurities, but at any rate, they're small particles. You can see they're kind of all suspended in the first vessel or tank that we're looking at in this graphic. The coagulant is added. This is going to allow the particles to combine into larger particles that will then settle out. In a conventional plant, we're going to get into some of the differences between what we want these larger clumps of particles or flock to look like between a conventional and a direct filtration plant a little bit further on in the presentation. So why do we need to do coagulation? Well, it's to remove the contaminants that are associated with these little particles. Microorganisms will be attached onto these little particles, and they can sort of hide. You know, a lot of these graphics that we've shown so far have been pretty cartoonish and have shown perfectly smooth spheres or something of that nature. But in reality, these little particles have a whole bunch of wrinkles, and they're not perfect spheres, and that gives a lot of area for microorganisms and viruses to hide. And so if we can remove the particles that they're attached to, then we also remove them. Natural organic matter, This is very important for our disinfection byproducts. We need to get rid of that organic matter so it doesn't react with our oxidant or disinfectant further down the process and end up creating disinfection byproducts in the distribution system. And then you get some aesthetic improvements too, in terms of maybe removing some iron or manganese or even some color from the water. And ultimately, it comes down to that what we practice in subpart H systems or full treatment systems is a multi-barrier approach. And removing these particles and having a properly operated coagulation and flocculation process is part of the multi-barrier approach that we use to produce safe drinking water. So these particles are so small, it can be kind of hard to visualize the impact that their size has on their behavior. Because they're so small, they have an incredible amount of surface area compared to their mass. And this provides great absorptive powers because they have you need surface area in order to absorb something. And when you have all of these teeny tiny particles, you end up having an incredible amount of surface area for absorption to occur. Like we discussed earlier slides, the disease causing organisms may be absorbed onto the surface of the particles and avoid disinfection. We're going to touch on this throughout this presentation, but coagulation and disinfection, these are contact sports, so to speak. And so, you think about disinfection, you're looking at contact time. Well, if some of these microorganisms are absorbed onto the surface of the particles, you may not get them in contact with your disinfectant, and they may be able to slip through the process. It's important to always keep in mind throughout the presentation that it is a multi-barrier approach, but each barrier relies to some extent on the previous barrier. So you've probably heard people say you can't disinfect something until it's clean. Well, that's because we need to remove these little particles where the disease-causing organisms might be bound up and able to avoid our disinfectant. Colloidal particles tend to have a negative electrical charge, and this is going to be very important when we start discussing the coagulation chemicals. You noticed on the second slide that we had those positive plus signs next to the aluminum ion. That positive charge on that aluminum is going to help to negate the negative charges on these colloidal particles. Because anybody that's played with magnets as a kid will know if you have two of the same charge poles and you try to push them, touch them together, they're going to push each other apart. And that's the same exact thing that's going to happen with these little particles that are all negatively charged. They get close to each other, that charge is going to repel them. They're not going to have collisions, and they're not going to start to stick together into larger particles. This graphic here on the bottom, I think, really can highlight the impact that the size of these particles has on the available surface area. You start off on the left, you can see we've got this 1 centimeter by 1 centimeter cube. It's got 6 square centimeters of surface area. Well, if you take that cube and you cut it up into 1 millimeter cubes, the surface area is going to go up by an order of magnitude, go into 60 centimeters squared, 10 times as much. Well, if you go down to 1 nanometer cubes, all of a sudden you're looking at 60 million centimeters cubed. So that is a 7 order of magnitude jump. Or, that's kind of hard to get your head around 7 orders of magnitude. I don't know if 10 million times more surface area is any easier to understand. But the point is the surface area just explodes as these, due to the size of these particles. So colloidal particles are ranging from 1 to 100 millimicrons, and these are tiny. They're not visible even with a microscope. Fortunately for us, they are larger than the average wavelength of light. And because of that, they will reflect a beam of light that's passing through the colloidal suspension. So because of this, we can estimate the concentration using a turbidimeter. And this is, we're really fortunate that they are large enough to reflect white light. And this allows us to sort of quantify the turbidity. I don't want to say easily, but there's a straightforward method to do it. And this little image on the bottom or cartoon kind of simplifies the process. You basically have a lamp or a light source. A lot of the turbidimeters these days are using lasers. The lamp light is focused through a lens that then goes through an aperture, which gives us a known surface area that the light is passing through. And that goes into the sample cell. And basically a portion of the light is going to make its way through the other side of the sample cell, and a portion of the light is going to be scattered, and we're going to measure that scattered light. And that is how we are going to estimate or measure the turbidity of the sample. And this has been the method that's been used for a very long time. Although, like I said, we've come a long ways in terms of what these turbidimeters look like. Some of the more simple devices that rely on this principle is like a Secchi disc. Some people may have those at the plant for taking a quick look at turbidity. And basically it's just the disc that has contrast in colors, usually black and white. Lower it down into a water column, and then you measure however far you can lower it before you can't see the disc anymore. And it's a way to quantify how turbid the water is. That's a really basic method that relies on the same principle. So how did they measure turbidity of a sample before we had the luxury of lasers and real-time automated systems? Well, here's one example, and I would call this eyeballing it. What we're looking at here is a Jackson turbidimeter. And basically the idea here, it's the same principle, but in this case, you have a light source, a candle, that's at the bottom, and you have a graduated cylinder, and you would keep on adding sample volume until you couldn't clearly see the flame any longer. And then based on how many inches of sample that took, you would be able to quantify the amount of turbidity. Now we're used to hearing NTU because this would have measured in JTU, Jackson turbidity units, rather than the NTU that we're used to seeing with modern equipment today. I just think that's interesting. It's certainly not going to be as accurate as the instruments we have today, and it's not going to be able to get anywhere close to the low levels that we can measure today. But I still think it's important not to totally dismiss the idea of visual observation. I mean, that's why operators are required to be present during filter backwashes. And also, a veteran operator can take a look at the flock basin and they can tell a lot just from a visual observation without taking any measurements. They're going to know if it's the flock that they want. It's going to be clear to them if the process is functioning as it should. So never want to dismiss giving it the eye test, I guess. I just put this up here because it kind of shows you that although the Jackson turbidimeter had its limitations, it is, possible to be able to look at these different samples and tell the difference in turbidity. I mean, I think most folks can tell the difference between 500 and 200 and 150, but then you get down to the difference between 20 and 10 and anything below 10. And, at least for myself, I wouldn't be able to distinguish the difference between those samples. But still, it gets you in a ballpark. You can know that you're less than 50 or, over 500 pretty easily, just by taking a look at it. So, what is the objective of coagulation? Our objective is to condition the particles so they can be readily removed in subsequent treatment processes. Removal of the particles reduces the waterborne pathogens, disinfection byproduct precursors, and color-causing compounds. An important thing to note here is coagulation itself does not remove particles or reduce turbidity. In fact, it often increases turbidity. So I think there's a few things here is that coagulation is just a conditioning process. It doesn't do anything to remove particles. And in fact, we don't want particles to be removed in the coagulation area. It's not designed generally for frequent removal of particles. So if you start getting particles building up in between your rapid mix and your flocculation area, that could be a maintenance issue. And also, it's probably not going to produce the type of flock that you're looking for if it's already forming up and falling out of suspension immediately after the rapid mix. Okay, so how do we accomplish coagulation? By feeding a coagulant or a coagulation chemical. The most common chemicals are iron and aluminum salts. So these metals have 3 positive charges, and a lot of times you'll hear them referred to as trivalent metal salts. Aluminum is going to be alum, and then of course there are 2 common types of iron salts out there. We're going to get into the difference between those and some of the subsequent slides. And also I would say that there are also polymers that can be fed as a primary coagulant. And also there are some complex forms of aluminum. The selection of what coagulant you're going to use really depends on your source water and your plant design. Sometimes people might even feed polymer seasonally or as needed, depending on if their source water fluctuates throughout the year. But in general, you're looking at alum and iron salts, ferric chloride, ferric sulfate. And this photo here is what I would say is a pretty typical setup for a coagulant feed system. You can see over on the far end, we've got this drum. This is our day tank. It's going to be fed from the bulk tank that's located somewhere else in the building. And over here is a sight tube. And the whole point of this day tank is to prevent an overfeed. And also it allows the operator to, when they're making their rounds, you can see they've kind of got this graduated with some zip ties. Not sure what the system is at this plant, but maybe each one is how much coagulant you typically would feed in a shift or possibly a day. And the operators, when they're making their rounds, can take a look. And this is just sort of a gut check. Does it look like we've fed about the right amount of coagulant since last time I made my rounds? And you can take a look at the site tube and know. yes, I'm 2 hours into the shift and I've used about, a quarter of what I'd expect. Or, on the flip side of that is I was in here an hour ago and there was the same amount of coagulant in the tank. Well, that's a red flag, probably a issue. Up here on the counter, we've got our 2 feed pumps. We got to have redundancy in case one of these pumps fails. There's another one that's ready to be put into service immediately. Typically, these will be the same model pump. In this situation, you can see that they're 2 different ones. My guess is one of the pumps failed. They decided that it was a little antiquated or that they'd like to change to a different model. And when the second pump fails, they'll probably go ahead and replace it with the same model. It's just convenient. If you have to switch right away, you can have the settings all set identical pretty quickly. It's also nice to have the same pumps just for parts and pieces, and everybody knows how to work on them. Just one more thing that you're going to have to know how to operate and fix if you have different feed pumps, but it's not, obviously, it's just inconvenient. It's not impossible or anything. You can see here, there's this little graduated cylinder and they've got a timer sitting here on the counter. And this is a calibration column. And basically it's a way to verify your dosage rate. And what you'll do is you'll fill that calibration column up, to a known volume, something that's easy to read, maybe 50 milliliters or 100 milliliters, nice round number. And then you can start your stopwatch and your pump at the same time, let it run for a minute, turn the pump off, and then you can see how much of the coagulant is left in the calibration column. Subtract that from your starting volume and you'll know how many milliliters per minute you're feeding. It's important to have calibration column. If you're relying on a scale or a flow meter, these are mechanical devices. They fail, calibrations go off. So it's nice to be able to have a concrete way to know, yes, I'm feeding the amount of chemical that I think I am. A few other things in this picture just to point out as long as we're here is you'll notice all the piping is orange. This is a 10 state standards requirement, and it's very helpful when you're in a plant. I'm sure you all have seen portions of the plant where there's a large number of pipes up in racks. They're going around corners. They're going up and down the wall. It's kind of hard to keep track of lines, and this color coding goes a long way to know to be able to follow lines and to know what you're looking at when you're out in the plant. So I think they did a very nice job color coding in here. Got some tiny little sections of pipe that aren't, but not a big deal. They're connected to the color coded pipes in short order, and they're directly off of the feed pump, so it makes it pretty easy to figure it out. So what chemicals are used for coagulation? Well, we've got our aluminum sulfate, very common, alum, ferric chloride and ferric sulfate. Those are your second most common coagulants, I'd say, at least in Michigan. Then you got some a little bit less common. You've got some cationic polymers. I have seen those fed as primary coagulants. You've also got complex forms of aluminum, polyaluminum chloride, polyaluminum silicate, polyaluminum sulfate, aluminum chlorohydrate. So these are a little bit more specialty. They're going to be more expensive. There might be good reasons to use them in your plant. It really depends on the design of the plant and the nature of the source water. Some plants might be really focused on reducing sludge production because maybe that's the limiting factor in their treatment process is the sludge recovery and sludge management equipment. There's a lot of different reasons that you might select a less common coagulant, but It's a little bit more detailed than we're going to get into during this presentation. Then in addition to your primary coagulants, you also have your coagulant aids. So these are polymers as well. You can have cationic. These are the positively charged polymers. That's why they're the only ones that can be used as a primary coagulant, because they have that positive charge that we need to neutralize the negatively charged particles. Got anionic coagulant aids. These are negatively charged. They can't be used as the primary coagulant. And you've got non-ionic. These are non-charged, and again, can't be used as a primary coagulant. They each have their role. I've seen plants that feed a little bit of polymer maybe in the spring if they're getting a lot of tannins or color in the source. Maybe they use a little bit to settle filters down after a backwash. Again, there can be a lot of really specific reasons that plants use a particular combination of primary coagulant and coagulant aids. Activated silica, this is an interesting one. This is induced turbidity. So basically in this situation, you're adding turbidity to your source water to aid in coagulation. And the theory behind this is maybe you're in Lake Superior or source water that has a very low raw water turbidity. With this, you're going to be able to add some turbidity, which is the theory is going to help you to get the collisions, help you form the larger flock particles that you're looking for. To be honest with you, I think this is kind of fallen out of favor. I don't see it very often or ever really. I don't believe there are any plants in Michigan that still feed silica like this. Although anecdotally, I have spoke with operators at plants that feed powdered activated carbon in the spring or summer for taste and odor issues. And they have said that they get lower turbidities in the finished water when they're feeding that pack. And they believe that it's probably because it does help increase the collisions and get better settling. And so there might be something to it, but a lot of folks have found that it's not necessary and it's kind of fallen out of favor. So where do these coagulants need to be fed? They need to be fed at the point of highest energy, at a location with the proper pH, not after feeding lime. We don't want the pH to be 10. And in the proper treatment sequence. Obviously, it doesn't make sense to have your coagulant added after flocculation. You need to go coagulation and then flocculation. The point of highest energy, it's an interesting way to phrase it, but typically what you're going to see is some sort of a mixing device that's going to create the energy needed to disperse the coagulant throughout the water column. Coagulation is a quick process. There isn't very much detention time. It needs to be very high energy because it's happening continuously. If you're just feeding a coagulant into a place that's very low or laminar flow, it's not going to get dispersed. If that coagulant doesn't come in contact with those colloidal particles, it's not going to neutralize their charges, and the whole process isn't going to be optimized and may not work at all, depending on how low of a flow we're talking. So there's a few different mixing options. We've got some that are sort of inline mechanical flash mixers, and that's gonna have basically like a little propeller and a motor that's gonna drive it, and that's gonna help disperse those coagulants. And then we've also got what they'll call a static mixer. And these are what we're looking at in this photo here. And again, it's really nice to see the color coding here. We've got our olive green. We're looking at some raw water here. We've got our coagulant piping. It's all color coded orange. And then you can kind of see in these two little spool pieces here, they've got these orange stripes around them. And so these are static mixers. If you had X-ray vision right now, you could look through that pipe and you'd see a series of baffles. And basically what that's going to do is it's going to make that flow very turbulent through that section of pipe. It's going to mix it all up, and it's going to help ensure that our coagulant, which is being added here, is going to get in contact with the entire water column as it's moving through. And it looks like here we've got 2 static mixers in series, and there's 2 different trains in parallel. So that's nice to have that redundancy. I'm not seeing a valve here to isolate one from the other, so it looks like it's going through both trains all the time currently. These are nice, they're static mixers are often viewed as having less maintenance, which I think is probably true. It's not a mechanical piece of equipment, so you're not going to have motor failures or need to replace propellers or anything like that, but you do need to take them out and clean them sometimes. And so it's nice to have them in a location where it's not, a week-long job to try and get that spool piece out of there without completely disassembling a bunch of piping. Just something to keep in mind. So let's talk a little bit about the sequence of how this coagulation is accomplished. So as we discussed, these little tiny colloidal particles carry a negative charge. And because of that, since they're all negatively charged, they're going to repel each other. And even if you mix them and they happen to contact, they're going to repel each other, and they're not going to stick together and form a flock or a larger particle. So the coagulants are on the other side, and they've got a very strong positive charge, trivalent metal salt, 3 positive charges. When they interact, they're going to cancel each other out. And the positive charges and the negative charges are going to disappear, and we're going to end up with neutralized particles. And at that point, when they collide, they're going to stick together. This is the term you're going to see a lot, agglomerated. It's a fancy way to say they're going to stick together, and they're going to form larger particles. These large particles are much easier to remove from the water, and that can either be from settling or from applying it directly to the filter. And we're going to want a different type of flock if we're trying to settle it versus if we're going to put it directly onto the filter. And the reason for that is when you're settling it, the big, large sweep flock is going to drop out of the water column faster than if you have a smaller pin flock. However, if you were to apply that large sweep flock directly on top of a filter, it's going to blind it off almost immediately because you're going to have the entire top of the filter covered in these big sweep flocks. So in that situation, you want a pin flock so that it can still be filtered out using particle attachment, but it's going to be able to use the entire filter bed because some of it's going to migrate deeper into the filter rather than it all just stopping on the surface. Going to get you longer filter runs. With the sweep flock being applied directly to a filter, you'd be backwashing so frequently, it would just be a really inefficient plant operation. Here's another one of our graphics. I think this does a kind of a good job of it. Again, it's just difficult sometimes when you're talking about something you can't see to understand it. So hopefully this helps some folks visualize it. You can see here, this is representing the negatively charged colloidal particles prior to coagulation. If you look really, really, really close, you can maybe make out that these are all negative signs around here. And basically you can see, yeah, they're contacting each other, but that charge is repelling. So even though they've come into contact, they don't form larger particles. On the other side here, we've gotten rid of all of the negative signs. We've gotten rid of that negative charge. So now when they collide, we are going to start forming larger particles, and that is our goal. So just another way to try and think about it. I've got a little video here. This is going to do a little demonstration. There's no audio on this. For those of you who are like me when you're a kid and you like to take a balloon and rub it on your hair or maybe your sister's hair and stick it on the wall, this demonstration is going to kind of use that same principle as another way to hopefully demonstrate the effect that these negative charges can have on the particle's behavior.
Hey, Andrew. We're not seeing anything. Was the video supposed to pop up?
How about now?
There it is. Perfect. Thanks.
All right, must be a little laggy or something. Thanks, Martin. So you can see here, both of these are negatively charged and they don't even touch each other and they're repelling one another. This is exactly the same behavior that these colloidal particles are going to have in suspension. Okay, so here we go. We're about to neutralize the charge. They're both attracted to it because it's opposite charge. And then once it's removed, the charge has been neutralized and they will actually come back together. I hope that is helpful for you. Let's see here. All right, so before we move on here, I want to just spend a few minutes on terminology because various textbooks and folks that you talk to might draw the line between coagulation and flocculation in a different place. And I just want to make sure we're all on the same page for this presentation. So for the sake of this presentation, we're going to look at coagulation as the chemical addition, the rapid dispersion or rapid mix, particle destabilization, which sometimes is also referred to as charge neutralization. On the flocculation side, we're going to pick it up right at the gentle mixing where we're just trying to get these neutralized particles to collide. Here comes that fancy word, agglomeration again. These collisions basically enable these particles to stick together and to form larger particles. This is what we would call our flock. And the larger particles quickly grow to being visible flock. And, this is what I was discussing earlier. Operator who's familiar with the plant operation is going to be able to look at that flock and know if both the coagulation and flocculation steps are working properly. The reason that this can get a little bit confusing, or people might choose a different, way to just use the term coagulation or flocculation, is because the line between the two is very blurry. When does flocculation begin after you leave the rapid mix? Well, it might be at the very tail end of the rapid mix basin. It might be a little bit farther into the flocculation basin. They're really it's the difference is the mixing speed, and that's going to decrease on a gradient. It isn't like a switch where you go from rapid mix, coagulation, mixing speeds, boom, to flocculation, gentle mixing. It's a gradient, and where you decide to draw the line between the two can be a little bit blurry. People might choose a different place. So we're going to jump into looking at some of the specifics of coagulation. We're going to look at the regulations. We're going to get into some of the chemistry, the physical processes, and then we're also going to spend some time talking about some myths that are out there, some sort of things that we've heard from operators or others in the industry, and just kind of understand where maybe where the myth came from, and also understand maybe why it's incorrect. And lastly, we're going to look at how do we monitor the performance of these steps. Again, I never want to dismiss the ability of an operator to visually inspect a flock basin and to assess its performance. I think that's a very useful and very legitimate way to do it. But on the other hand, you know, before coagulation, you can't see these particles. You have to rely on surrogates measurements like NTU or turbidity measurements. So there are some unique ways to monitor the performance, especially in the steps where visual observation doesn't really do you any good. All right, so here we go. The Code of Federal Regulations, Part 141, Subpart H. And a lot of you may have heard your full treatment plant being referred to as a Subpart H system. Well, this is where that comes from. That's the section of the Code of Federal Regulations that discusses conventional and direct filtration plants. This is also where you're going to see the requirement to add a primary coagulant at Subpart H systems. And the reason for that is that basically the performance is measured based on removal credits for pathogens. And a Subpart H system must meet turbidity limits and provide full treatment, including coagulation, for conventional and direct filtration plants in order to be able to be awarded those removal credits. And you know, this is probably the most common place where you've seen this is when you're looking at your contact time requirements. You need to get 3 log removal. You know, if you're at a conventional plant, you're going to get 2.5 log removal credit for having a properly functioning and operated coagulation, flocculation, sedimentation, and filtration steps. And then the remaining half log is going to be made up by your disinfectant. You're getting your CT. For the direct filtration plants, they don't have the sedimentation process. So they're only awarded 2 log removal credits. And they're going to need to make up an entire log removal credit with their disinfection or through CT. And just, you know, log removal credit, that doesn't necessarily mean a whole lot unless you're familiar with the term. But when you're talking about log removal, 1 log is going to be 90% removal, 2 log is going to be 99% removal, and 3 log is going to be 99.9% removal. So I don't know, maybe that's easier way for me to think about it. Maybe it's easier for some others too. So aside from the federal regulations, we've also got Act 399 here in Michigan. And I think Act 399 actually is a little bit more straightforward in some ways than the Code of Federal Regulations. And I really like this section right here. It just says, a sufficient primary coagulant dose shall be added to create a settlable or filterable flock at all times that a conventional filtration or direct filtration plant is in operation. So I think that makes it really clear. If you're running the plant, you have to be feeding a coagulant. It surprises me sometimes that folks don't know that, or that you can get confused that whether you need to feed a coagulant constantly or not. But I really think this section of Act 399 makes it pretty clear. Now, the one part of this that's a little bit softer, I guess, is a sufficient primary coagulant dose. Well, what's sufficient? You have to kind of, since this is the foundation of the treatment process, you kind of have to look at how the rest of the process is performing to know whether you're feeding a sufficient dose or not. You know, are you getting settleable flock if you're in a full treatment conventional plant? Are your filter runs where you expect them to be if you're in a direct filtration plant? Is your filter effluent turbidity where it needs to be with the regulations? And even more than that, is it optimized and we're removing the maximum amount of turbidity possible? Because, you know, the more turbidity you can remove, the less disinfection byproduct issues you're going to have, the less potential for sedimentation of these remaining turbidity in your tanks and your distribution system. It's just all the way around. The more turbidity you can remove, the better. So try not to think of the turbidity requirements as once you hit that, you're good. And you want to, that's the most you're allowed. You want to try to reduce it as much as possible. So yeah, the sufficient dose really takes a more holistic look at the treatment plant to determine whether it's a sufficient dose or not. And that's why maybe this language had to be a little softer in the act. So I like this chart. It's a little bit busy, and I'll just kind of explain it a little bit. All these different symbols represent different combinations of coagulants and source water quality. So you're looking at low turbidity, raw water, medium turbidity and high turbidity. And we've got both alum and ferric, and it looks like they've even got a polymer in here. And down here on the graph, what we're looking at is our cryptosporidium log removal, like we talked about, 90%, 99%. And down here is our turbidity. And you can see, as you can imagine, the more turbidity you remove, the more crypto you're going to remove. But what I think is interesting is when you look at the where we're getting pore removal down here in this bottom corner, not exactly sure why they decided to make this very weird looking polygon here, but sure, is it's not any one combination that's getting poor performance when your coagulation process is off. It's not just, high turbidity raw water. It's not just low turbidity raw water. It's not just alum. It's not just ferric. Basically, if you don't get that coagulant dose and the rapid mix right, regardless of what coagulant you're using or what your raw water quality is, you're going to end up down here in this corner of poor performance. And so that's really the point of this graph to me. And the other important thing to remember is, we use turbidity as a surrogate. And it does a good job at that, because the more turbidity we remove, the more cryptosporidium in this case we're removing. And it's important to remember that coagulation is an important part of making sure that we remove pathogens and disease causing organisms from the water. It's not just disinfection. In fact, disinfection is going to be much more difficult if you don't have good coagulation on the front end of the process. Okay,
Hey,
so
Andrew.
Yeah.
You don't mind? Do you mind if I break in right now, because we're getting close to our break time and second poll question time? Is this good?
Yep, perfect.
9:30. Okay, okay, good. All right, everybody. So give Andrew a quick break here, and we are going to run our second poll question. So I'm going to launch that. And just one. Oh, go ahead.
Yeah, and while the poll question is running, everyone, Andrew, we do have one question. Is there any cons or downfalls of dosing alum? And I know you talked at the beginning of your presentation that relates to the selection of alum depending on the quality of water that you are processing.
Yeah, there are going to be, I don't know, it's hard to put it into pros and cons. It really, you know, somebody's con is another person's pro, depending on your plant setup and your raw water. But there are definitely some reasons that you would want to move away from alum sometimes. And we're going to get into this a little bit when, depending on the alkalinity of the raw water, maybe you don't have enough alkalinity and to use alum, but you may be able to use a different coagulant with the alkalinity you have available. Otherwise, you might have to supplement your alkalinity if you're going to use alum. I think also depending on your process, you may be looking at sludge production, and maybe you need to use some polymers because otherwise you end up having too much sludge volume. And then I think also one of the things that maybe is a little bit less technical but still very important is just economics, and some cases it's going to be more cost effective, even though a polymer might be more expensive per unit. You're going to end up with cost savings because of something like sludge production, or maybe there's just some really large treatment plants that are nearby yours that are using ferric, and you're able to do bulk purchasing with them to get a better price. I mean, there could be a lot of factors that go into that, I suppose.
Awesome. Thanks, Andrew.
Thanks, Andrew. And just want to let everybody know we're going to close up this poll here. I've had it on for quite a while now. And let's share the answer. And we're kind of all over the place here, Andrew. So maybe you can let us know what the answer is. Ways to determine the optimal coagulant dose include all the following except.
Well, add color to distinguish the flocks is the one that I would go for probably. I mean, I'm sorry I didn't touch on jar testing. That's a very common way for folks to evaluate different coagulants. I should have touched on that. Of course, the visual observation we discussed, and we didn't get into zeta potential yet either. So maybe the placement of that poll question was a little different in previous presentations. We didn't quite make it as far as other folks did before we presented that, but luckily you don't have to get it right, so don't worry.
No, you don't have to get it right. Just answer the question. All right. Okay, Andrew, so we're going to give you a break and give the team here a break and let you all have a break. So we're going to go on break for about 8 minutes or so. So be back here at 9:40. So 9:40, we will resume and continue on with our presentation. So we'll take a break. Thank you. Okay, everybody, looks like we're at about 9:40. Hopefully you all had a quick break, chance to stretch your legs for a minute. Andrew, are you back?
I'm back.
All right, if you want to go ahead and share your screen again, we can get back at it.
All right. All right, everybody seeing my screen?
Yeah, looks good.
All right, thank you. All right, so jumping back in here, we're going to talk a little bit about enhanced coagulation. So, this refers to the process of reducing disinfection byproduct precursors in conventional treatment. So plants that can't meet the alternative compliance criteria must practice enhanced coagulation to reduce TOC. What is what does this term enhanced coagulation mean? Well, typically that's accomplished by higher coagulant doses and reduced pH. And something we haven't touched on, and this is actually an excellent point I should have made during the pros and cons of feeding alum, is each coagulant is going to have a pH range where it's effective. And alum has a pretty narrow pH range where it's effective compared to ferric. So that would have been one of the disadvantages, perhaps, of alum if you have a hard time staying within the optimum pH range. So TOC is what is our precursor for disinfection byproducts, and it can be removed through coagulation, flocculation, and sedimentation. But like turbidity, it has a coagulant demand. So if the coagulant doses aren't made to account for changes in turbidity and TOC, then your performance will suffer because, perhaps you have steady turbidity, but you have some dissolved organic carbon that you're not picking up in the turbidity and you're not accounting for it in your coagulant dose, then the coagulation is going to suffer. And as we've discussed, if the coagulation suffers, then all of the subsequent steps are also going to suffer. Okay, so this is a little bit busy, but what we're looking at here is the red line is the plant's alum dose over time. You can see on the bottom axis here, we're looking at days. And the green line is UV 254 meter. Not everybody has one of these, but we're gonna focus on why it's a useful tool here. And then on the bottom is our turbidity. And again, turbidity, we're using it as a surrogate for a lot of different things, and it's very effective and it's very useful. But if looking at this graph, you can kind of see there was a spike here in the UV 254, and there's a little blip on the turbidity, and they're reacting by increasing their dose when they see that. And it tracks it pretty closely. The peaks tend to line up. This big one tends to line up. This one tends to line up. But you'll notice on this last spike, we picked it up on the UV 254, but the turbidity was completely, if we were just looking at our turbidimeters, we would have totally missed this spike. And that's basically what we were getting at in terms of TOC and dissolved organic carbon, is you're not going to pick that up on a turbidimeter and you'll be going to be kind of blind to it. Now here at this plant, they were watching their UV 254, and you can see they did increase their alum dose to account for this spike. But if they wouldn't have had the UV 254, my guess is that the alum dose would have been left constant, probably somewhere down here, and the coagulation in the plant would have suffered, and the plant performance in general. Now, that's not to say that they're not going to hit their regulatory requirements and put out acceptable product. It's just that it's not going to be optimized. And this just kind of shows the usefulness of these UV 254 meters. Okay, so now we're going to start to get into some of the chemistry a little bit. So before we took a break, there was a question about, what are some of the drawbacks or disadvantages of dosing alum? And something that's important to understand is that all coagulants consume alkalinity. So I guess I should back up one step. Coagulation chemistry is very complicated and it's not fully understood. You know, I went to Michigan Tech years ago and that's what they told me then. And this is, 14 plus years later, and that's still what they're saying. So it's very complicated. And a lot of these formulas that we're looking at are kind of boiled down version of what's actually happening, that kind of summarize the general processes. But in general, the coagulants are going to consume alkalinity in the process, and you need to make sure that you have a sufficient amount of alkalinity in the raw water for these reactions to take place. Otherwise, you're not going to form floc and the process isn't going to work as designed. Also, you can see that what we have here is some carbonate hardness. This process is going to transform that carbonate hardness into non-carbonate hardness. And it's very similar. Up on top here, we're looking at the reaction for alum. You'll notice this 14 H2O, that's known as the waters of hydration. That value can fluctuate a little bit, but it is commonly 14 is used. It's kind of the general rule of thumb, waters of hydration for alum. And then down here, we've got the ferric chloride reaction. And we're going to get into this in the subsequent slides here, but you can notice we've got 1 mole of alum reacting with 3 moles of this alkalinity. And down here, we've got 2 moles of ferric chloride reacting with the same amount of alkalinity. And that'll be important in the subsequent slides. Key points: alkalinity is consumed. This goes away on the right side. Precipitates are formed. That's what this right here is. These are your floc. That's what this complex is. And for those of you who maybe have had some chemistry courses, this downward facing arrow in the chemical formula is letting you know that this is no longer in solution and that this is going to drop out or settle out of solution now. Carbon dioxide in the water is going to form carbonic acid, which is going to cause the pH to go down. As things become more acidic, we move down the pH scale. So that's a lot to take away from these 2 lines of chemical reactions. But like I said, it's a lot more complicated than this, but this is the key points. Okay, so we're going to get into a little bit more of the molar ratios that I kind of touched on the previous slide. So from this equation, 1 mole of alum reacts with 3 moles of alkalinity. What they're doing here is 1 times 594. They're starting to look at the molecular weights of these, each of these compounds. Parts of alum will react or remove 3 moles, and you'll see, so this was 1, because we have 1 mole of alum, 594, that's the molecular weight of alum. 3, that's how many moles of alkalinity we have, and each mole weighs 100 parts of alkalinity. So when you start getting down here, you can look at the ratios between alum and alkalinity and ferric and alkalinity. And so you have 2 to 1 with the alum and 1 to 1 with the ferric. So sufficient alkalinity is necessary for coagulation, but it's also important to have sufficient alkalinity after the treatment. And that's because low alkalinity water doesn't have much buffering capacity and it's a lot less stable. And you don't want to be putting out an unstable water into your distribution system because that can lead to corrosion problems. We kind of touched on this a little bit earlier, but some places up here on Lake Superior, you're going to have kind of a low alkalinity source water, and you might have to adjust the alkalinity in order to make sure that you have enough to get these reactions to go to completion, and also so that you end up with enough alkalinity left over so you don't end up having a corrosion event in the distribution system. So the amount of alkalinity consumed can be estimated by the ratio of 5.6 milligrams per liter of alkalinity being removed for each 1 milligram of coagulant as aluminum ion. So basically that's a lot of, on the previous slide, we were looking at this in terms of alum. Now we're looking at this in terms of aluminum ion and iron ion. And why are we looking at it from that perspective? It's because ultimately we're trying to achieve charge neutralization. And so the element that's doing the heavy lifting in these compounds is this trivalent metal, aluminum or iron. That's really what's important for our dosing, is to make sure that we get enough of these ions introduced to the source water so that we can neutralize those particles. So if we get caught up looking at the weight of alum or the weight of ferric, we always need to keep in mind that really what we're looking at, or our goal here, is to get enough of these ions into the water to neutralize the charges. So for aluminum, you're looking at 5.6 milligrams per liter of alkalinity being removed for each milligram per liter of coagulant as aluminum ion. And the amount of alkalinity that's being consumed for iron ion is 2.7 milligrams per liter. So this is interesting because on the previous slide, we were looking at the mass of the entire alum molecule rather than just the aluminum. And so here you can see we've got Al2. So there's 2 aluminums here and there's 2 ferrics here because there's 2 moles of ferric chloride, whereas in the alum, there's 2 aluminum ions in 1 mole of alum. But if you were looking at it here, you would think that it's 2 to 1 alum to alkalinity. That might lead you to believe that alum is going to consume less alkalinity. But when you start looking at it in terms of just the aluminum ion, you can see 1 milligram per liter of the aluminum ion consumes 5.6 milligrams per liter of calcium carbonate, or that's what we're using for alkalinity here. That's what they're saying, alkalinity as CaCO3, whereas 1 milligram per liter of the ferric or the iron ion is only removing 2.7. Also, even though these formulas, it's actually on the previous slide, highlights this a little better, but you can see that your carbonate hardness is being transformed into non-carbonate hardness in this process as well. So the charge on the dissolved coagulant species and the relative amount of floc formed are a function of pH. Therefore, the pH at which the coagulation occurs is one of the most important parameters for proper coagulation performance. So now we're kind of getting into, coagulation is the foundation of the treatment process. and having the right pH is one of the key foundational aspects of being able to optimize your coagulation. And the pH of your source water very well may impact your choice of what coagulant chemical to use. And we're going to take a look at some very busy graphs, but we'll try to boil them down a little bit on the next few slides. There is an interrelation between the pH and the type of aluminum or iron oxide that is formed. And depending on what type of oxide is formed will determine the charge on the oxide complex. And basically, all of this goes to say that if you're forming the wrong or not ideal oxides, then they're not going to perform ideally in the subsequent treatment steps. Okay, so this looks like some abstract art, right? But I guess you'd say you've heard science mimics art sometimes, and this is definitely one of those situations. For the time being, we're going to just ignore everything that's underneath this line down here with the zeta potential. And we're just going to focus on this upper portion of the graph that's sort of like a V. So looking up here, we've got this little circular portion of the graph. This is where we're going to form the optimum sweep flock that we'd be looking for in a conventional plant. On the bottom here, we've got our pH of the mixed solution. So in this case, we're looking at what the pH is after the coagulant has been added. This chart is what's known as a solubility chart, and this one is for alum. In order to interpret this chart, you can look at the pH and then move up vertically to see what type of dose is necessary to achieve the charge neutralization and or to get to this sweep flock, if that's what your target is. So you can kind of come over here and you can see the center of this is probably somewhere in the neighborhood of 7.5 pH. And if you went up, you could see over here how many moles per liter you would need in order to get into this range. Well, it looks like over here they've got it with, see here they're using 14.3 for the waters of hydration. I don't know. Like I said, it fluctuates a little bit. You're going to see a few different values used for that water of hydration. But this is a lot easier to interpret because the units over here are milligrams per liter. So you can see this is not a linear scale on this side, but let's just see. This is probably about 65. So we're probably in the 50 neighborhood in order to get to the center of this circle at a 7.5 or so pH. But what's important to look at is these little shaded areas and where these arrows are pointing. These are the different types of oxides that you can form, and they behave differently. And also, we've got this general V outline here, and basically anywhere within this V is the acceptable pH range for alum. And as you can see, it's pretty narrow. And especially when you're trying to hit this little window right here, you're really looking at between like 6 and, just over 8. This will be important when we look at the ferric version of this graph next. I guess I'll also just mention that the optimum pH for alum is commonly assumed to be, 5.5 to about 7.8. If you're feeding outside of that range, it's going to be inefficient at best. You might be able to get the job done, but you're not going to be optimized. And so we all want to get optimized in order to remove as much turbidity as possible, but also to reduce costs at the plant. And that can be from, if you can reduce how much sludge you're forming, if you can reduce the frequency of your filter backwashes, if you can reduce the amount of coagulant that's required, all of these things can help reduce the overall cost of operating the plant. And it's not a technical topic necessarily, but it's still a important topic for everyone to consider, especially if you're in a position where you're looking at the budget for the plant. So also, I guess I'll just point out that this sweep flock occurs at the elevated end of the alum dose and in this very specific pH range. And this is sort of what we talked about a little bit when we were on the enhanced coagulation. It's you can't be feeding your coagulant after you've done lime softening and you're over 10. It's not going to work. So making sure that you understand what the pH of your water is when your coagulant is added is very important. So coagulant solubility, the dose must exceed the coagulant solubility limit. We want this stuff to fall out of suspension. The alum must precipitate for flock to be removed by settling or filtration. We don't want to just have enough coagulant or alum in solution so that it's dissolved and then it passes through the system. It passes through the settling basin and ultimately through the filters. And there are potential health effects. And you may also end up with it falling out of solution or precipitating in the distribution system if you, for instance, have a pH adjustment before it goes out into the distribution system. As far as the potential health effects, aluminum, we don't usually think of that as contaminant of concern, but there have been some studies looking at linking it to Alzheimer's, and it's just generally not a good idea to have it making its way through the system. We want it to fall out of suspension and get removed before it gets into the distribution system. Okay, so this is a similar chart, but we're looking at this for ferric now. As you can see, it's a similar situation where we're at the upper end of the dose and we're in the middle / lower end of the pH zone to get to the sweep flock or sweep coagulation, they're calling it here. But one of the first things that just jumps off the page at you is look at how much wider this V is for ferric. It has a much, much wider range of pHs. And even this target area for sweep flock spans a much wider range of pHs. So this could be one of the reasons that you decide to go with ferric instead of alum. The effective pH range here is 5.5 to 8.8. And basically the moral of the story is if you have a higher pH source water, or if you're doing some sort of a process before you get to coagulation that elevates the pH, then alum may not be the best choice, and you may want to go with a ferric because it's going to be a lot more effective at those higher pHs. Okay, so what are the mechanisms in coagulation and flocculation? So charge or neutralization, we've talked about this a lot. Basically, the positively charged coagulant comes into contact with the surface of the colloid that's negatively charged, and the charges are neutralized. We've got colloid entrapment. This occurs when the coagulant is fed in excess of the amount needed for neutralization, creating floc capable of enmeshing colloids. And basically, this is when we're getting into the sweep floc. We have pin floc when the charges are neutralized. We start getting these flocks enmeshed into these large sweep flocks. That's what we're referring to colloid entrapment. And now the last step here is bridging. And this can occur when the coagulant forms threads or fibers that bind several of the colloids together. So this is beneficial because it helps it resist shear forces. You know, we're mixing the floc gently after we've conditioned the particles because we want the collisions, but we have to be careful because if there's too much mixing, the floc that we've worked so hard to form can be broken up. So if the mixing energy is too high in your floc basin, you can end up breaking apart that floc that we've worked so hard to form. And that's why generally when you're looking at a flocculation basin, you're going to see the mixing velocity decrease as you move through the basin. Generally, some high molecular weight polymers are real effective at causing the bridging, and it gives you know, you think about a polymer, it's a long chain of carbons, and that is sort of the thread-like fiber that they're talking about here in this definition. And here's another little graphic for us to try and visualize this. In this case, these spheres are sort of our floc that we've generated, and they basically start to get attached or tangled up in these polymer threads, and that's making a larger and more stable floc that's going to be more difficult to break up. Over here, we're looking at our sweep floc. They're all enmeshed, but they're not necessarily as strongly connected as they would be if we had bridging occurring. So basically, the bridging and the charge neutralization are the primary mechanisms for coagulation that we'll be discussing. All right, we'll see if my luck is any better with this video. Hopefully it goes no problem here. I thought that did a nice job of summing it up. And again, just another way to try and visualize what's happening here. Aside from some of the cartoonish pictures that I've been sharing too. I don't know, I'm more of a visual learner myself, so it's helpful to see some of these graphics. Okay, so here we go. We're going to get into some of the differences in objectives between direct filtration, where we don't have a settling process, and conventional treatment plants where we are going to have settling. So it basically comes down to which coagulation mechanisms are we going to use. In both cases, we're going to use the destabilization, but we're going to stop there for direct filtration. We're not going to go on. We're not going to try and hit that sweep floc section of the solubility graphs we're looking at. We're not going to be adding polymer to try and create bridging. We just want to destabilize those particles to create a filterable floc. And what do we mean by filterable? Well, filtration is achieved by particle attachment, not straining. Straining is what you have in a membrane plant, where it's particles are excluded based on their size. In a granular media filter, we're relying on particle attachment. So what we want to do is create a flock that doesn't have all these negative charges so that it can attach to the filter media itself. We also don't want to move on to the sweep flock because, again, we don't want to blind off the top of that filter and have to be backwashing so frequently that it makes the plant inefficient to run. So for sweep flocculation, we do the destabilization. This is what we're doing in a conventional plant. But then we're also looking to get the sweep flock. We're looking to get the bridging. And that's so that we can settle it out in the settling basins, the majority of the turbidity. And then we can go ahead and apply whatever turbidity is remaining. These are going to be the smaller particles. They didn't settle out to the filters where they'll be removed by particle attachment. So the idea is that all the big particles will settle out. Whatever makes it through the settling basin are going to be smaller sort of pin flock type particles that then can be pretty efficiently removed by the filter. Similar to drawing the line between coagulation and flocculation, I mean, all of these mechanisms are happening simultaneously and in various degrees. So it is possible that you're getting a little bit of sweep flock in your direct filtration plant, or that, you know, you end up having some particles that remain as pin flock coming into your settling basin. And that's really when we're getting into, you know, optimizing your process. Basically, the ideal coagulation method is going to be based on the source water quality. And once you can evaluate this using jar testing, and you can look at what is the best coagulant to achieve my objectives, what is the best mixing speed to achieve my objectives. And also, you know, that has to fit into the limitations of your plant design. And it's important for operators to understand the different types of coagulations and what a method is appropriate for their plant. What is the goal at their plant for the coagulation step? Okay, polymers. Again, only cationic polymers can be used as a primary coagulant. We need those positive charges. That's critical for a primary coagulant. If it doesn't have those positive charges, we don't consider it a primary coagulant. And as we looked, Act 399 requires all plants, subpart H plants, to continuously feed a primary coagulant. So if you're going to feed a polymer, you need to make sure that it's cationic. Otherwise, you're not going to be in compliance. These are more expensive, but sometimes maybe some of that cost can be offset because you can have reduced sludge volumes using a polymer, and you might not have to adjust the pH as much as you would if you're trying to use like an alum, for instance. There's a lot of different ways to classify polymers. You know, looking at the charge, that's what they're referring to as type here. You know, cationic, positively charged; anionic, negatively charged; non-ionic. Molecular weight, as it was mentioning during the bridging discussion, the heavy polymers are good for bridging. Molecular structure, you know, that's an important part of the bridging too, is if you have these long thread-like structures, then that gives a lot of opportunity for the colloids to attach to it. And the charge density, how much, you know, how much charge is it carrying? Some of them carry none. So you might have some that are positive, but it's not very positively charged, and others that are very positively charged. And selecting when to use those really depends on what you're using the polymer for. Okay, now we're going to take a look at some of the myths. Here's the first one. Coagulation is not important for low turbidity source waters. Well, we are very spoiled in Michigan because we have the Great Lakes. And in some cases, you know, the turbidity in the raw water meets the requirements for finished water turbidity. And that, you know, logically can lead to the question, why are we even bothering to try to remove this remaining turbidity? And the reason is because even though there's might be low turbidity, those particles are still potentially carrying disease-causing organisms that we need to remove in order to ensure that we're providing a safe product to the customer. And also, I think it's important at this point to remember what happened in Milwaukee. You know, even though we are sort of spoiled or fortunate, if you will, to have such high quality source water in the state, one of the nation's largest water disease outbreak happened with Great Lakes water in Milwaukee. And they were meeting the safe surface water treatment rule requirements at the time. Basically what it comes down to is that we just don't have the luxury to be complacent and to say that the raw water turbidity is so low, we don't need to worry about coagulation because it's already meeting the finished water quality. It's part of the multi-barrier approach, and we need to make sure that we're removing those pathogens. And one of the ways we do that is by implementing coagulation to remove the particles. So this one, it's easy to understand how a person might think that, but coagulation is very important regardless of the source water turbidity. Just to summarize this, turbidity is an indicator. It doesn't tell us if there's disease-causing organisms present or not. Even low turbidity water can have disease-causing organisms in it. Even if you do meet the compliance levels, it doesn't mean that you've eliminated the risk of pathogens. That's what we were just talking about with Milwaukee. And then also some of these pathogens are becoming resistant to conventional disinfection. So we, you know, need to do ourselves as much of a favor as we can by removing them as early on in the process and not relying solely on that disinfection step. And that all plays into the multi-barrier approach and why it's so imperative to ensure that we are able to produce safe drinking water. Okay, so this is actually from a study that measured cyst levels, not just turbidity. So they weren't looking at our indicator turbidity. They actually measured the cyst levels before and after treatment and found that even with low turbidity, proper coagulation resulted in greater removal. So just hammering home, this has been looked at in more than just a theoretical sense. And they went beyond relying on turbidity as an indicator and actually measured cysts and found that, yes, the theory is correct. And just a little bit more concrete evidence that low turbidity source water still requires coagulation. We've been talking a little bit about particle attachment. We're going to take a little look at what that means. So this series, we're going to click through a few different images here in a second, is going to sort of depict the process of particle attachment and demonstrate that it's not straining. the particles that we're trying to remove are not going to get stuck in these spaces between the filter media. Instead, what happens is they come into contact with the filter media and they sort of coat it and attach to the outside edge. As you can see, these could easily fit through between here. And they start building up. All of a sudden, you're going to start seeing more and more, you're going to need more and more head to push your water through the filter. And we're starting to get to a point now where we're probably looking at getting close to a filter backwash because all of the attachment sites are taken, and now we are actually starting to do a little bit of straining. I really like this picture a lot. It can be kind of hard to understand what's happening here, but this is from a scanning electron microscope. And what we're looking at here, you can kind of almost see right here, this is one big sphere. There's one over here. And then there's at least one on the bottom. Maybe there's two. It's kind of hard to tell. But those big spheres are your filter media. And all this little tiny fuzzes, or whatever you'd like to refer to it as, are actually the turbidity that we're removing. And so you can see this is a giant chasm, basically, where these tiny little particles would have no problem at all flowing directly through there and not being removed by the filter if they hadn't been conditioned and had their charges neutralized so that they would actually adhere to the surface of the filter media. Down here in the description, it says that these are small particles coagulated with a cationic polymer, that's our positively charged polymer, and retained on the filter sand grains. This is after 3 hours of filtration at a depth of 46 centimeters. So that also just shows you again, like we were discussing, you don't want to apply that sweep block to the top of the filter because then you're not going to be able to take advantage of all of the surface area which these turbidity can adhere to. If you apply that sweep block, it's all just going to blind off the top of the filter and you're not going to be able to take advantage of your filter depth. When the coagulation is optimized, the particle removal, it can be optimized as well. However, even once you get to this point where your coagulation is optimized, you're getting great filtration, they're all particle attachment is occurring, it's still susceptible to upsets. And that can be caused by sudden flow changes through a filter. If all of a sudden there's a big hydraulic event on this filter, a lot of these particles might become dislodged and move past the filter. To better understand the relative size of the cryptosporidium cyst to a sand particle, there's a good analogy. It says, think about increasing the size of a cryptocyst to the size of a 6-foot person. Now expand the size of the filter sand particle by the same proportion. How tall would the sand particle be? It would be about the same size as an 80 to 100-story building. So if these cryptocysts were the size of a 6-foot tall man, then these sand particles would be the size of an 80 to 100-story building. And that just goes to show you that when you have all of your sand particles packed together in your filter, there's easily going to be spaces between them that are much, much larger than the cryptocysts. And they're going to be able to easily pass through in between those particles unless the charges have been neutralized and they want to adhere to the surfaces of the media. So rapid mixing. We touched on this a little bit when we looked at the photo of the inline mixer. But when we're looking at coagulation, we're talking about rapid mixing at high speeds. It's a short detention time, really high energy. You need to inject the primary coagulant into the point of highest mixing energy. directly up gradient of a static mixer, directly into the blades of a mechanical mixer, for instance. They look at mixing energy as a velocity gradient. Units can be weird sometimes. So the velocity gradient is expressed as inverse seconds. The mixing speed should be adjustable on whatever device you're using. However, I would say static mixers kind of fall short on this because, you know, it's all dependent on what the flow rate is. Maybe they could be adjustable in the sense that if you have multiple mixers that are in parallel and you're in a low flow situation, maybe you can turn off one of the trains and force all the flow through one mixer and in order to increase the energy. But that's one of the shortcomings of a static mixer, is that you're not going to be able to just walk over to a dial and turn the speed up like you could on a mechanical mixer. Here's when I was talking a little bit about the inline mixers. It's basically here we've got our injection. It's injecting the coagulant directly into the blades of the static mixer, and that is dispersing it throughout this water column. Sometimes you have a rapid mix basin. So this maybe has a little bit more detention time. Water has to come into this basin. The coagulant's being added right down here by the blades, so it gets exposed to that high energy mixing zone before it's able to leave the basin. The detention times are very quick. Here we're talking about less than a second. Here, maybe we're talking about 30 seconds. Bottom line is that the detention times for coagulation are much, much quicker than they're going to be for flocculation or sedimentation. Here's that static mixer that we saw a version of in the photo. You can kind of see here, this one's got all of these baffle plates, making that water snake its way through up and down, side to side. It's also making the flow very turbulent through that section of pipe or that spool piece. There are some other designs out there. You can see this one's just kind of up and down. There might be some plants that have been designed to just have sort of like a overflow of a weir where it's added. I don't think that's very common anymore. Maybe in some cases you'd see a drastic reduction in the pipe size, and that could induce turbulent flow and be a potential place to inject your coagulant. Again, these are nice. There's no mechanical equipment, but the downfall is they're not very adjustable. So maybe if you're at a plant that operates at pretty much the same rate all the time, not a big deal. But if you're going to want to be able to adjust your treatment rate, this might not be the best fit for you. So here we're looking at a little bit of a different setup. And here's where they have the chemical feed, and it's basically has nozzles. So instead of just feeding the chemical into the mixer, these nozzles are actually going to make it come out at a little bit higher pressure. They're going to force it in the opposite direction of the flow, and that's what they're going to rely on to get their mixing. It's more adjustable perhaps than a static mixer, but maybe still not as adjustable as a mechanical mixer. And then over here, we've got a clarifier. We see these in Michigan, pretty common. And here the coagulant is meant to be added in the center portion of the clarifier. This is known as the mixing zone. You can see this one has a mechanical mixer at the top. So here's where your rapid mix occurs. And then as soon as you exit that, you start to get into your flocculation zone. And these are pretty slick because you've basically got coagulation, flocculation, and settling all occurring in the same vessel. And you can kind of see down here, they're depicting these arms. This is going to be scraping up all the solids that are accumulating in the bottom of the clarifier. getting them into this sump. And then this can be commonly referred to as a sludge blowdown. So there be a valve somewhere here. They can open up that valve and the hydraulic head will push that sludge out of the sump. So pretty common. I guess one thing, these are susceptible to thermal upsets sometimes. So if you have drastic change in water temperature, that can be an issue for these. So here's another myth. Rapid mix isn't necessary if you can get the same turbidity removal without it. So this comes up a lot of times when the rapid mix is broken. And they say, well, why should we fix it? We're getting the same turbidity removal. So the issue here is that you kind of incorrectly conclude that the rapid mix is not needed. But the reality is, without the rapid mix, you're not properly coagulating the water, and you can compromise your removal credit under the surface water treatment rules, and you may be in violation. So again, turbidity is a surrogate. It's a very useful surrogate, but at the end of the day, we need to make sure that we're doing proper coagulation so that we are removing as many of these pathogens as we can prior to the final disinfection barrier. And, just like we touched on with the low turbidity source waters, just because you're hitting your turbidity goal doesn't mean that you've necessarily removed as many of the pathogens as possible. Also, you're likely not optimizing your processes if you're not using the rapid mix, and there might be some cost savings associated with that, especially depending on if you end up having to do a lot of backwashing or something because your coagulation and flocculation isn't optimized. Again, turbidity is just an indicator. The multi-barrier approach is imperative in water treatment. We don't want to be relying on that final disinfection step. Take advantage of all of the barriers we can get. Also, we've talked a little bit about the removal credits. You earn those credits by having a properly designed and operated plant. So if you're going to you need to have a rapid mix if you're going to be able to earn those removal credits. And then there's the other coagulant objectives too, which again, we can talk about disinfection byproducts. We can talk about color removal. There are other objectives aside from just the pathogen removal. So why is rapid mixing important? The intermediate products of the coagulation reaction drive neutralization. So there's going to be, we looked at those chemical formulas. We'll look at some more a little later on. There's going to be intermediate products that are only there for a short time. That's a part of the reason why coagulation chemistry isn't fully understood. They're only there for a short time, but they're important because they're neutralizing the particle charges. Again, microseconds prior to reacting further, because as soon as that charge is neutralized, that product's no longer present. It's been changed. You need to have that coagulant dispersed rapidly throughout the water column to achieve effective destabilization. These things need to come into contact with one another. It's not enough for them just to both be in the water column together. They need to come into contact. Rapid mixing also causes transport and collisions of colloids and coagulant. So we were just talking about contact sport. High energy mixing is imperative in direct filtration plants. You're not going to get the benefit of having flocculation steps. Medium energy and longer detection times are sufficient when sweep coagulation is predominant. And finally, it's just, at the end of the day, it's a compliance requirement. You need to do it. It's in the rules. This figure shows the intermediate species that are only present for an instant or so before the reaction is completed. The final metal hydroxide precipitates are formed ultimately, and that's what we saw in some of those earlier equations that we were looking at. They're a little bit simplified. The intermediate species are the most effective at charge neutralization. And if they're not transported throughout the entire water column very quickly, because they're only around for a little bit, then the coagulation is greatly reduced. So you need to get those intermediate products dispersed throughout the water column before they disappear in order to make sure they contact the colloids that we're trying to remove. So how are we going to be measuring our coagulation performance? Jar testing, streaming current / zeta potential. Well, let's back up. We didn't really touch on jar testing. So jar testing is a very common way for plants to simulate the processes that are taking place, and it's a good way for them to evaluate changes, what the potential impact of changing mixing energy is going to be, what the potential impact of changing coagulants is going to be, feeding a coagulant aid. Basically, you get your jar testing apparatus set up. You know, some of them are circular, some of them are square jars, and there's a mixing blade within them. And you get that calibrated for how your plant is operating currently. And once you've done that, then you can start to make changes, and it'll give you an approximation of what those changes would, the impact those changes would have on the full scale plant. So that's a good way to try to monitor or optimize your coagulation process. Some of these other, like a streaming current meter or UV 254, these are looking at the actual process itself in real time. And we kind of looked at that UV 254. If you don't have something like that and you're relying only on turbidity, you may not have the optimal coagulant dose because you're kind of blind to some of the aspects or some of the water quality parameters that a turbidimeter is not going to inform you on. You can always look back at records. So you can see, hey, last time we had a spring thaw and we had a lot of runoff, what coagulant dose we were using and how did that translate in terms of our finished water turbidity. So looking back at records is always very helpful. And then we get back to this visual observation. I really, like I said, I don't want to downplay this. There's a lot of new technology that's available and it's very useful, but ultimately a experienced operator is going to be able to do a visual observation at different points. You could do it in the flock basin. You could grab a sample in a beaker and bring it back to the lab. Some facilities might have a camera set up looking at the flock basin. So anybody that's in the control room can kind of just glance over and take a look, make sure that it generally agrees with the information they're getting back from their monitors. Because again, monitors, meters, these are all machines that are subject to failure or falling out of calibration. Whereas, you know, similar to the sight tube on the day tank, it's a gut check. You can look over and say, yep, that lines up with my meters and I'm feeling confident that they're functioning properly.
Hey, Andrew.
Yeah.
It's Jim again. Just wanted to break in because we're at the next point for our next poll and break. Is okay?
Oh, absolutely. Yep.
All right, everybody. Well, let's take another poll here. I'm going to launch it. And Martin, if you see any questions or anything that might have coming up for Andrew, just let us know.
Awesome. Thanks, Jim. We did have a couple questions. They have all been answered. So at this time, we are A-OK.
All right. So I'll see the poll question up. There's a third poll. What is the objective of coagulation? And then after this, we are going to take a short break. Okay. Hopefully everybody I've left it up there for over a minute now. Hopefully you all had a chance to answer the poll question. I am going to end it. And Andrew, you want to give us the answer on this one? Looks like most people chose option A.
Yep, no, that's right. And I can understand folks that went for answer number 2. We do need rapid dispersion of coagulants, but the objective is to condition them for removal in subsequent steps. So glad to see people got that.
All right. Okay, everybody, we're going to take a quick break. Let's take about a 5-minute break. So get up, stretch your legs for a minute, be back here at about 10:45, and we will resume. So we're on break until about 10:45. Thank you. Okay, everybody, we're back. Just wanted to make sure we all got a short little break in there. And I'll check in on Andrew. Andrew, you back too?
Yep, made it.
All right. All right. All right. We're in a home stretch here. So Andrew, go ahead and share your screen. And just want to remind everybody that we're going up till about 11:45 today. So got about another hour. And if you have questions, type it into the question box. I know Martin's here and he's been answering a lot of them behind the scenes. Also, yeah, if you look in the chat, I dropped a copy of the presentation in there. Most of you should have gotten it in an email when you registered, but there's also a link to the presentation in there as well. So Andrew, looks like we see your slides and we're ready to go.
Thank you. All right, so let's get into another one of our myths here. And, this one is coagulation performance monitoring isn't necessary if you feed excess coagulant. And, you can remember from those solubility charts we looked at, as the scale wasn't linear. So as you fed more and more and more, you weren't really getting, it was diminishing returns. So the thinking here is, you know what, if 50 is optimum, let's just feed 100, because then we don't have to worry about it. We'll have enough and it won't make any difference. Well, too much coagulant could actually reverse the particle neutralization, causing floc to break up. And this makes perfect sense, right? Our initial problem was, well, we had everything was negatively charged. We're trying to neutralize that negative charge. If we continually add positively charged metal ions into the mixture, eventually the particles are going to become positively charged, and we're going to have the same exact problem that we had when everything was negatively charged. Feeding too excessive of coagulant is unnecessary, and it's not economical. I don't think the whoever's in charge of the budget for the plant is not going to be happy to hear that you just run the feed pump at maximum capacity, because that way you're getting enough of a coagulant dose. It's not as effective, and it's certainly not cost effective. Also, the coagulant contributes to the sludge volume and the mass. So excessive coagulation or coagulant dosages can overwhelm the dewatering, storage, or disposal processes. A lot of times too, you're looking to land apply your sludge. And so if you end up having elevated metals because you've got a really high coagulant dose, that may start to impact your disposal options. And it's a lot more economical to have these solids land applied than it is to pay to put them into a constructed landfill. So these are important things to consider. This is a nice little chart. It just kind of shows that as you continue to add more and more coagulant, you can see your turbidity is dropping, and eventually you hit this relatively flat portion of the curve. And this is what we were looking at on the solubility chart when we were, it wasn't a linear scale on the dosage. And as you got higher and higher, you weren't really getting anything out of it. Well, that's exactly what this flat section is. You could feed more and be here, but you wouldn't see any improvement in terms of turbidity removal. It's fine to overfeed in here, but you're not gonna, it's not economical. You're not really getting any benefit out of it. It's better to try and target right here where you're using as little coagulant dose as needed to get sort of the optimum turbidity reduction. And then you end up way out over here. You actually are going backwards. And this is exactly what we were talking about. You know, if this continued off to the right, we'd see this come back up in sort of a bell curve. And if you were just way overdosing, you could almost end up back where you started. So this is just another graph that sort of illustrates this point. And you can kind of see here, this is basically an inflection point. Right here, you can see this curve is increasing. The slope is getting steeper and steeper and steeper. Boom. You hit this point, it's still, the line is still going up, but the slope is starting to flatten out. And when you hit that inflection point, if you drop straight down on the filter turbidity graph, you're going to end up at the very start of the, you know, safe dosing range with the operational goal or the optimized dose being right at the very beginning of this flat portion of the curve. All right, we're going to move on to flocculation. Flocculation follows coagulation and precedes settling or filtration. So again, conventional plant, flocculation, then you move on to your settling basin, plate settler, whatever it may be, a settling step. Direct filtration, you're going to go skip that settling step and you're going to go straight to filtration. Flocculation is accomplished by subjecting the water to prolonged gentle mixing for about 30 minutes. So we're talking about coagulation, we're talking about extremely high energy, really fast, rapid mix, lasts a second, lasts 30 seconds, just a very quick process. Then we're following that up with the flocculation, much slower mixing energy, much longer detention times. This gentle mixing is just to get these neutralized particles to collide and to start forming whatever our desirable flock is. Just, you know, if we're going for pin flock, if we're going for sweep flock, if we're trying to get some bridging by adding a polymer, it kind of depends on what our goal is and what type of flock that we want. Ultimately, though, there's some important things to keep in mind here is that you don't want to have, if you're trying to get a sweep flock or a bridged flock, you don't want to have high mixing energies in your flock basin. It's going to break that flock up that you work so hard to create in the subsequent steps. Again, conventional treatment, you want as much of that turbidity to settle out in the settling basin. It's going to get you longer filter runs, and it's easier to remove the sludge a lot of the times from the settling basins than to manage the filter backwash water, depending on where it's going. And to do that, you want a large, dense flock. Makes sense. You want the surface area to go down and the density to go up. These little particles, huge surface area, low density, that makes them want to float, makes them difficult to settle. We want lower surface area, higher density. Direct filtration, you know, we're just looking to get rid of that charge, maybe increase the size a little bit, but we don't want big flock because we need to be able to take advantage of the depth of our filter. And if we apply a big, you know, large sweep flock to the top of the filter, we're only going to be able to take advantage of the very top surface area of the filter. None of these particles are going to be able to migrate down and adhere to the particles, the media that's at the greater depths of the filter. So looking at some flocculation basins, these two are very similar. This one, we've got a vertical mixing apparatus in here. Just gonna kind of turn this water up. You can see they've got boards on these arms. This one is the same thing, it's just horizontal. A key thing about these boards, so basically on these, you've got a couple different ways to adjust the mixing energy. You can change the velocity that the motor is turning the mixer, or you can remove boards from the mixer. And oftentimes that's what you'll see when you have multiple steps in your flocculation basin, which we're going to look at here on the next page. So what we're looking at here is a 3-stage flocculation basin, and these are basically baffle walls. So on the first one, the bottom of the baffle wall is open. Second one, the top of the baffle wall is open. Third one, the bottom is open again. And this is going to increase the residence time because now the water has to take this sort of snaking path and it can't go straight through. It's also going to reduce short circuiting. So if you've got a bunch of flow coming, directly into the middle of this basin and you didn't have any baffles, a lot of it would just go straight through the center and you'd end up with sort of dead zones on the sides. These baffle walls are going to help with that. Here, it looks like they're using the speed of the mixers in order to reduce the energy. So you start off here again. This is the velocity gradient. So we're in these weird inverse second units, but you can think of it in terms of mixing speed. So the first basin is going to be, even though it's all gentle mixing compared to the coagulation step, it's going to be the fastest mixing. It's going to get slower and it's going to get even slower. And the reason for that, again, is that at the beginning, we've got smaller particles. We're just trying to get those collisions. But as we move on, now we've formed these bigger particles and we got to be careful so that we don't break it all apart because we've worked so hard to get it large enough to settle. So that's why we're reducing the mixing energy from one end of the basin to the other. Here's an image of a actual flocculation basin. You can see here again, they could add additional boards on here. This one is a chain drive. So you can see the sprocket chain. It's going up to a drive motor up here. Sometimes that's why you might want to use different number of boards on them, is maybe you have the same drive. So it gives you the ability to be spinning it at the same rate, but have different amounts of mixing energy. Down here in the basin, you can see there's some doors, people doors. You can access here, make repairs, clean it out if you get a little bit of sediment building up. And also these baffle walls, these are baffle walls. They're just a little different design, and basically that's there for reducing the amount of short circuiting that you're getting in the basin. These solids contact clarifiers, these are, again, these accomplish coagulation, flocculation, and settling all in one unit, which is nice. Much reduced footprint compared to if you got a rapid mix basin, flocculation basin, settling basin. We can put all of those in one unit here. The coagulant is either fed in the rapid mix unit upstream of the clarifier or directly into the center mixing zone. It looks like you can see maybe there's a drive here for a mixer. Maybe that's our rapid mix on this cartoon. The coagulated water is then mixed with an upflow stream of highly concentrated, well-grown flocks. In that turbulent zone, the collisions occur and the incoming microflocks are absorbed to the surface of the grown flocks. This reduces the flocculation time, and the larger, heavier flocks settle out, forming a defined sludge blanket. In order to overflow the effluent weirs, water must move upwards through the sludge blanket, which has a filtering effect. Again, one of the issues with these, they're great. They're a lot smaller footprint. Problem is they are a little bit susceptible to thermal changes, which can lift the sludge blanket, causing the flock to carry over. So basically, just to kind of go over, you come up here, you're feeding your coagulant rapid mix. Now we're into the flocculation area, a little bit slower. Here, these are solid walls or a skirt. So the water has to go underneath this skirt. And what we've got here is a bunch of very mature, big flock. And those little flock particles are going to hit these larger flock particles. They're going to agglomerate or stick together. And the largest ones are going to drop out. So this is almost, it's almost like a filter in a way. And one of the problems is if you have a big temperature change, either this blanket can fall or worst case, the water coming in is denser and it lifts this blanket up and you end up getting carryover through the troughs and onto the filters. And I think there was a time when these were very common on the Lake Michigan side of the state, and some of the plants there had issues with thermal upsets and moved on to different designs, plate settlers, conventional flock basins, things like that. But they can be very effective, especially if your source water isn't subject to very much temperature swing. Sedimentation step. In this step, gravity is used to settle out the flock. I mean, this is can be done in a few different ways. We're going to look at that in some of the next slides here. In the most simple sense, you can think of a large open basin. And basically, you can look at the water column and how deep it is and do some calculations to understand how long that basin has to be in order for there to be enough time for the large particles to fall from the top of the water column to the floor of the basin. And that's exactly what we're talking about as far as effective settling times. There can be a flow pattern to provide adequate detention time at peak flows. So, it's impractical maybe to build your basin just as an open basin because it'd have to be unrealistically long in order for there to be enough detention time for the particles to settle out. So instead of doing that, we'll put in some baffles, make that water take a serpentine flow through the settling basin. Maybe similar to that flock basin that we saw, make it go up and down and take a serpentine flow that way. And it basically makes the residence time for those particles increase without increasing the dimensions of the flock basin. The goal here is to eliminate as much of the turbidity as possible before filtering. We've got an area-wide optimization program your plant may participate in. It's an EPA program. Michigan's involved. Several other states are involved as well. And basically what this program does is we set their goals that are set for each step of the process. And for settling to be considered optimized, the goal is to have less than 1 NTU 95% of the time. And, just as a quick plug for the AWOP program, I look at it and to some extent is like compliance insurance. If you're meeting those AWOP goals, then you're going to be going above and beyond what's required by the regulations. And also by tracking this information, and for those of you who have seen the graphs and the data that's produced coming out of their workbooks, you can really get a sense. Maybe you've got 2 settling basins and you might realize one is outperforming the other, and it might lead you to make adjustments to your process to increase the effectiveness of one of the basins. Ultimately, you don't know what you don't measure. And the AWAP program is just a way to put to use a lot of the data that you're already collecting, and it can lead to improved finished water quality and potentially some cost savings too. And like I said, it's almost like a compliance insurance. You know, if you're meeting the optimization goals, then you're going to be meeting the regulatory requirements as well. Take a look at a couple different settling basin configurations. This one is sort of the conventional basin. Get your influent coming in here, and you can see there's sort of a scraper board. This is going to travel on chains, and it's going to pull that all of the settled block back here into this, I'll refer to it as a sump, I suppose, where you can draw the sludge off as it accumulates. So we'll take a closer look at these scrapers in a few minutes. And then down here on this end, you've got your effluent troughs. So there's going to be perhaps a weir here, and the water that overflows the weir is ultimately going to be the water that's headed to the filters. We got a little cross-sectional view here. This is kind of helpful just for the operation of these scrapers. Basically just travels on this chain, pulls all that sludge back into this sump. And similar to the other photo that we looked at, there'd be a valve here. When you open it up, the head pressure from the water that's above it can push that sludge out of this pipe. I've heard mixed reviews on these scraper systems. Some folks like them. Some folks seem to have more maintenance issues than they'd like, I suppose, is the way to put it. You can think if this blade gets a little crooked or one of the chains starts to stretch a little bit more than the other, it can start to jam up, not function properly, and cause some headaches. So what are the benefits of optimizing our sedimentation? Why would we want to focus on optimizing our sedimentation? Well, the big reason is whatever we can remove in sedimentation doesn't make it to the filters. And if we can reduce the filter loading, then we're going to be able to go longer between backwashes. And increased filter runs, less backwashing, makes the plant more productive during a shift. You're going to generate more water, produce more water in a shift if you don't have to backwash as frequently. You're consuming water for your backwash, that filters offline. It's not making water during the backwash. You may have to do filter to waste. It's a lot easier to remove turbidity from the settling basin. It's got equipment in there to remove it than it is to go ahead and try and remove it from the filter with a backwash. And again, if you are in a plant that has multiple settling basins, you really should be looking at the turbidity from each train individually to evaluate the performance. Seen some situations where maybe there's some interesting piping coming into the influent side of a basin, and because of that, then, it's not a distribution header maybe between the two basins, and because of that, you end up getting a lot more loading on one basin than the other. So you can end up having a lot more turbidity pass through the basin with the higher loading than the one with the lower loading. And maybe that could all be rectified by adjusting a valve and forcing more of the flow into the second basin. Just because they're identical design doesn't necessarily mean that they're going to have identical performance, because the loading could be different between the two units. And you might not know that unless you were evaluating both of them. Of course, if you have a continuous turbidimeter that's data logging, that's going to provide you with a lot more resolution than grabbing grab samples occasionally throughout a shift. Some other reasons to look at optimizing sedimentation, you can reduce your filter effluent turbidity, especially if you're removing more of the more particles you can remove in the settling, the better. And perhaps you can also reduce your coagulant dose if you can optimize your coagulant dose. Let's put it that way. Perhaps if you optimize your sedimentation. So this looks like an outdoor basin. I say that because I can see a bunch of grass growing through it. And this is an example of those scraper bars that we see. And again, I've just gotten mixed reviews on these. I've heard some plants say that they just love them and they've never had a problem, and it's a simple technology. And I've heard other folks say those are a nightmare and they just really didn't work for us. Here you can see the scrapers are returning on top of this iron rail, and then they drop down onto the concrete floor, and here's where they'd actually be removing the sludge or pulling it back to that sump that we saw in the previous pictures. Know how many outdoor plants we really have in Michigan. I think I could think of one, but definitely not common, and it's kind of unusual to see the grass growing up in the bottom of a sedimentation basin, but there you go. Another example of a sludge removal device is this sort of a siphon equipment. And basically the way that this works is there are orifices or openings on the bottom of this bar, which is kind of like a header. And what'll end up happening is this gets drug cables, probably cables, along the bottom of the basin, and the head pressure from the water above it pushes the sludge up into that header and out into whatever type of sludge management system you have. A little bit different design. Again, I think it just kind of depends on your plant. I've heard people say they like these too, and I don't know, it's just kind of your preference. I think at the end of the day, sludge is just not a convenient sort of material to manage. It clogs things up. It gums up mechanical components, and it's not fun to deal with when you need to make repairs. So I think ultimately people's preference really just depends on their experience with how much maintenance they have to do. Nobody really wants to be doing a bunch of maintenance in this, working with the sludge in these basins. All right, so I mentioned that I've seen it seems to be quite a few plants that have basically taken their conventional settling basins and retrofitted them to have plate settlers installed. And the advantage of the plate settlers is that the settling time, the amount of time it takes for a particle to vertically travel from the top of the basin to the bottom of the basin, is greatly reduced. And also, you can see these inclined settlers have an advantage because there is just a ton of surface area here. Each one of these is a metal plate. You can see how many are stacked up here. And so basically you can achieve the same amount of settling within this within a much smaller footprint. You know, if you wanted to accomplish the same amount of settling, you're in a conventional basin, it would have to be significantly larger than what we have here in this plate settler, inclined plate settler. I think this is a really cool demo, and it kind of demonstrates how this works. Let's see if it works. Are you guys able to see my screen?
Yep, we can see it.
All right. One in a row. So the magic is sort of in these plate settlers, or the mechanism that makes them work so efficiently, is you'll notice on the vertical column, the sediment or the particulates had to drop the entire length of the vertical column before they were settled out. On the inclined plate settler, they only have to drop basically the width of the tube before they hit the bottom. And once they come into contact with that surface, they start piling up on top of each other, and they start sloughing off down that glass or whatever, these stainless steel plates. And the speed at which they slough off down that surface is much faster than the rate that they drop through the water column. Like so many things, it seems so simple, and somebody much cleverer than me was looking at it and realized how to take advantage of that, and it's been a pretty important development, I guess, in settling technology. And it's in, you know, so many things that we've talked about today, you can't see them. It's hard to visualize. It's hard to understand. So it's really nice when you can see something that's so clear and easy to demonstrate how it works with a inclined plate settler. Here's another image of one of those retrofit projects that I was discussing. I think this is one of them that's along the Lake Michigan shoreline. I've seen a few of them like this, but you know, you can't really, there's not a whole lot to see when you're actually at the plant, but the amount of difference that this makes is just huge. The footprint of the facility is greatly reduced, and the amount of residence time in the settling basin is greatly reduced to accomplish the same goal as a conventional settling basin. I know there are several consultants that have really done quite a few of these retrofit projects, and at least the operators that I've spoken with have been very happy with them, pretty impressed. I think, you know, there are some, maybe, I don't want to call them drawbacks, but you can imagine that occasionally you have to clean these plates. And so there's a little bit different operation and maintenance challenges with plate settler than there is with conventional settling basin. But on the whole, I think everybody's more than happy to spend the additional time required to clean these plates and keep these plates functioning properly compared to the alternatives of having a much larger basin in order to get the required settling time. I think also some plants, demands increase, and this may be a way that allows them to keep the same plant building or same plant footprint, but to increase the plant capacity. So there's a few different applications for it. All right. So I kind of like this graphic. I'm not necessarily I'm not endorsing any products here, but these folks had a nice diagram out, so I thought I would take advantage of it. And I really like this one because you can see these are the flocculation chamber, and they've got vertical baffle walls so that they're having to take that serpentine path through here. These are all on chain drives. And this one I like because you can see they've got 3 boards on here, 3 boards on here, 2 boards on the last one. And that's what I was referring to as far as being able to have 2 ways to reduce your mixing energy, reduce the speed and reduce the surface area of your paddles. They've also come a long ways with these paddles, the boards, if you will. They've got new materials that they make them out of. For a time, they were made out of materials that would degrade and rot, and they'd have to be replaced. That's gotten better. Also, in some situations, you may have 2 of these treatment trains that are directly next to each other in parallel. And what can happen is sometimes you can use the same drive to operate both basins. So there would be another basin just behind this. You might have one drive that's turning both of these, this stage of the flock basin, and for each one of these. I've seen that be pretty common, I suppose. Here, I think this is something that is also pretty common. It's almost like the opposite of a weir in a sense, but the water comes in and you can see there's all these little holes drilled into this trough. And that's basically just making sure that the water gets evenly distributed across the entire length of the basin, and that we're not ending up with all of it just dropping out at the first end and having a big dead zone over here. They do the same thing on this side. A lot of times I've heard operators refer to this as like a Swiss cheese wall. They put holes in the concrete wall at the end. It's going to help distribute the flow. Sometimes they'll even, if they know that they have more loading on one end of the wall than the other, then on the end that receives more loading, they'll make the holes or the penetrations smaller diameter. And that just kind of, and then larger diameter on the low flow side. And that just kind of helps to equalize the flow into the next phase of the treatment plant. So pretty interesting. I think it's kind of fun to see different setups. And then of course over here, you can see that basically what's happening is the water's coming through, it's hitting these plates. And as we saw in the demonstration, it only has to fall the distance, the particles only have to fall the distance until they hit the plate. And then once they do, they're going to slough off to the bottom. Whereas in a traditional basin, they'd have to settle this whole length. So particles starting here only has to fall until it hits that, boom, it's down, rather than settling all the way down the entire column vertically. And once it hits these plates, the water that rises up ends up in these collection troughs down here into this large collection trough, and then that's headed to the filters. Similar to, you know, conventional settling basin or even a clarifier for that matter, there is going to have to be still be a sludge collection component. And that is being accomplished in this system. Looks like they have those vacuum headers that we saw in some of the others, where this is going to be able to travel down the bottom of the basin, and it's going to rely on the head pressure from the basin to push the sludge in. Now, you know, looking at pros and cons here, I mean, if there is an issue with that sludge collection system, it could potentially be more difficult to work on it. You have to get down underneath these plates. You know, if you have to get that entire header out of there to make some repairs, that could be challenging. So a lot of times though, you will see man doors in these baffle walls so that once the basin is dewatered, you can enter pretty easily. And if the designer was, if you're fortunate enough to have considered that in the design, then hopefully the man doors are large enough to easily get the equipment in and out and that sort of thing too. Something else that's important on these retrofit projects though is these are heavy. You know, the weight of these plates has to be considered. And it could be that the foundation of the settling basin, you know, wasn't originally designed to accommodate those loadings. So they see a lot of the designs that also include considerations for what the foundation needs to be able to support, and you know, what the supports for all those plates need to look like and need to be able to handle. So it's, even though it's common in a retrofit, I guess there is some extra considerations compared to if you were building a brand new plant from scratch with this design. Typically the plates are all stainless steel, and it's kind of neat when you see the design because it's really about the projected area of the plates, and that's how they're able to reduce the footprint, is based on the surface area of the plates that's being exposed to the flow direction. But very interesting. Fortunate enough to see several of these plants, and who knows, maybe we'll see more of the clarifier plants that are struggling with thermal upsets moving away and going in a direction similar to these plate settlers, because in a lot of ways they provide the same advantage as the clarifier in the reduced footprint of the facility. I'd like to open it up if we have any questions. Do we have any questions, Martin?
Hey, Andrew. Yeah, we did. If you could go back to slide number 11. This is like a multi.
Whoa, back to 11. Well,
Back to
excuse me.
11.
Well, I hopefully don't give anybody motion sickness here. All right.
So for this one, Andrew, one of the questions was, what is the use and primary purpose of the coagulant aid? That's question 1. The second one is, what is the purpose of the organic polymer when using the anionic, aka the negative charged type of polymer, since the primary purpose is to have a cationic or a positively charged coagulant to kind of attract that negative particles. So it's kind of like a multi part question.
Yeah. So as far as the coagulant aids go, I think a good example of this, or one that I've heard, a good example that I've personally heard, is we had an operator that was at a plant, and it was a Great Lakes plant, but the intake was located near a series of, I think, 5 rivers that all came into Lake Michigan, all in this one pretty small area. So even though there was a Lake Michigan plant, the water quality was really dictated seasonally by the water quality in these rivers that were feeding the lake. And so in this particular area, they had a lot of swamps, a lot of cedar, a lot of trees that produce tannins. And so what can end up happening is when it's spring runoff, you get a lot of color in the water, and it's not wasn't being addressed by their primary coagulant. So they ended up getting in touch with their supplier, and a lot of times the suppliers will do jar testing and other evaluations to help you identify products that can get you to your water quality goals. And in this case, that was to remove the color. And so the supplier did a series of jar tests, and they were able to identify a coagulant aid that they feed seasonally that just drastically increase their ability to remove the color. And they don't have to feed much. It's just a little bit that they add in addition to their primary coagulant, and it removes the color. There could be a lot of other reasons that you select a coagulant aid. Some of them we touched on a little bit in terms of you want to get bridging. Maybe you don't need bridging necessarily, but if you add a polymer, you get the bridging, you get a more robust or structurally sound flock that isn't likely to break apart and is likely to settle quicker. So that's another example of where you might want to go with a coagulant aid. As far as the non-ionic and anionic, the coagulant aids generally aren't being fed at the same rate as a primary coagulant. So even though it might have an anionic charge, it's not necessarily being fed because of that property. And because it's being fed at such a smaller rate than the primary coagulant, it doesn't necessarily upset the charge neutralization process that we're really targeting with the coagulation step. Like I said, a lot of times folks that are feeding coagulant aids have run into kind of a unique problem, or they have a sort of a secondary goal for their finished water that they're unable to meet, maybe like the color issue. And they've ended up reaching out to a consultant or reaching out to their supplier. And the supplier or the consultant, of course, is exposed to a much larger number of plants. So they may have already seen this problem and have some ideas, or they will maybe start from scratch doing some jar testing, getting some of the raw water from the plant and really dialing in specific coagulant aid to help them meet that specific objective that they're struggling with.
Awesome, Andrew. So yeah, so then the just kind of a little bit of a recap, the coagulant A doesn't necessarily is not necessarily involved in the in the neutralization of the particles, but can aid in certain aspects such as color, as you stated. So great, great. Another question: what is considered too frequent of a backwash?
Well, I think that that is kind of plant specific in a way. Um, you know, selecting the backwash frequency is varies from plant to plant. Some plants will look at backwash in terms of, well, we only run this plant for one shift a day, and it's an 8-hour shift, and that's all we need to make to meet our demands. And so our practice is at the end of every shift, we backwash so that the plant is ready to go for the next shift. Other plants will look at it from a time standpoint, and they'll say, well, we know that a backwash is going to be required after, let's just pick a number, 20 hours online. And so we're just going to backwash the filters after 15 because we don't necessarily want to get close to that, to when it's actually needed. And other plants will look at the rate of the water production. And when a filter reaches a certain production level, they'll decide to backwash the filter in order to increase their production. The amount of time that a filter can operate in between backwashes really depends on the filter. Some filters have a huge surface area and have a significant capacity for particles to be attached to them. Others are a much smaller footprint and they're going to require more frequent backwashing. I think the answer is a little bit complicated, but it really boils down to, can you meet your demands with the required backwash frequency that you have? Do you, if it's not optimized, are you generating a bunch of backwash water that you now have to dispose of sort of unnecessarily? There's a lot of drawbacks to not having it optimized. However, I don't know that we can necessarily put a exact number on what's too frequent. Unfortunately, it's a little bit plant specific in that sense.
So Andrew, yeah, great, great
Hey,
response.
Martin and Andrew, I'm gonna, while we're waiting to see if any more questions come up, we're running close to the end of the time here. I'm gonna throw up the last poll.
Awesome, thank you, Jim.
Yeah, so just the last poll question of the session. If you go ahead and answer it. And I don't know, Martin, I don't see any more questions in the queue. Did you have any other ones?
Yep.
Okay.
We have to go to 11:45
Okay.
for operators to get their CECs for the time on this session. Absolutely. But yeah, Andrew, the other question is, can you talk a little bit about, and it's slide number 40. And it's the inline mixer versus a rapid mix basin. Which one would be best for the mixing, and how one would be implemented versus the other?
Well, I think that they could both be optimized they both definitely could be optimized to achieve the velocities and the detention time required for coagulation. So you could use either one. I don't know necessarily that there's a best between these two. What I would say though is, you can just look at the graphics that we have on the screen here and see the size difference. On one hand, you're going to need an entire basin that's going to be taking up square footage in your plant. It's going to require that you have a larger plant footprint, and the inline mixer just takes up a small section of pipe similar to a spool piece of pipe. I'd say the other thing is that, some of the drawbacks of an inline mixer is that you can't really observe it, can't really observe the mixing process. So if something's going wrong, you're not going to be able to really give it a visual inspection. And that's one of the advantages of the rapid mix basin, is that you can actually observe the process to some extent. I think they're, in this case, they're both adjustable in terms of being able to adjust the mixing velocity. So they're pretty much equal in that sense. I do think that, again, this comes back to that photo where we had the inline static mixers, but you have to make sure they're in a place where it's easy to service the equipment for the inline mixers. And as long as that is met, I do think that it's probably easier to service the inline mixer. You're not going to end up with maybe having some dead zones in the corners and some sediment building up, or you don't have to worry about potentially having a confined space entry if you need to go in here to service the mixing equipment in the rapid mix basin. With the inline mixer, you can just remove that spool piece. You can remove the mixer directly out of the that section of pipe to service it. It is a little bit easier in that sense.
Okay, awesome. Thanks, Andrew. Thank you so much for answering the questions. I think that was about it. Is there anything else you'd like to add on the whole process of coagulation, sedimentation, flocculation for operators to kind of take away from the presentation?
Well, one thing I am curious about is, how do we do on the last poll question?
Yeah, I'm sharing them right now. So I'm sure everybody's wondering, flocculation is accomplished by what?
Wow, well, it looks like we got the majority of folks got the answer correct. It looks like, though, there's a little bit of confusion about the mixing speed. Just want to repeat that when you get to flocculation, you're looking at gentle mixing. So we definitely don't want mixing the water rapidly to promote additional collisions. And then it looks like a few folks had adding additional coagulant. Typically, that's not a part of the flocculation process. So maybe just a little mixed up. Again, the terminology is important and they kind of blend together, but especially for the sake of taking exams and things, it's important to make sure that you have the terminology correct. I think the final message and closing on this whole presentation is just subpart H treatment systems rely on the multi-barrier approach in order to ensure that we remove pathogens from the water, and coagulation is the first step in that multi-barrier approach. And ultimately, it's the foundation of the process. And if you don't get your coagulation right, there's no way that you're going to be able to optimize any of the subsequent steps. The performance of the entire plant is going to suffer if you don't get that coagulation step correct. So that's probably the most important aspect of this entire presentation.
Awesome. Thanks, Andrew. Yeah, with that said, yeah, we're right on time, almost 11:45. So thank you so much, everyone, for joining us. Jim?
Yeah, all right. Hey, thanks, Andrew. That was a great presentation. Sort of wrapping up session 2 here of the series. Thank you, Martin, for handling all the background stuff and answering those questions. In the chat, remember there is a link to the presentation if you want to download it. Also, we sent an email out to you with the links as well. So yeah, our next session is on Monday, starting again at 8:30. So be ready on Monday, bright and early. You'll get an email again from us ahead of time with links to the presentations and materials and all that good stuff. So make sure you're ready for that. For this session, again, we will be following up with details on the session, including a link to the recording. So you have that. If you missed a part of it, or you want to, I guess, save it for later, you'll be getting that in the next, I think, day or so. We'll try to get that out as soon as possible. Just a reminder on CECs, give us some time to process all those. It does take a couple weeks, so don't be expecting to see those anytime, you know, the next few days. It'll take a couple weeks, so be on the lookout for those later. Just want to remind everybody, you're going to be hearing us plug this again and again, I guess, probably. The Water Infrastructure Conference registration is open right now. That's September 19th to 21st in Kalamazoo. It's a great opportunity to network with fellow water operators and get a lot of good information. A lot of good information from a lot of different sessions. So consider attending that registration. The early bird rate ends at the end of the month. So just want to put that out there. All right. Hey, thanks everybody for joining us today. And I hope you have a great rest of your day. Thank you.
Thanks, everyone.